Ladies and gentlemen, good morning. In this lecture, last lecture from the linear transformation chapter, we will talk about the transition matrices and similarity. In fact, the second part from this lecture, which will be about similar matrices, is very important when we will talk about the diagonalization of matrices, and we will relate this to eigenvalues and eigenvectors. Well, fortunately, I already have the notes written, so I'll just go through them and explain them. We will start with the matrix of a linear transformation. And we will see how things that we learn in chapter 4 about the transition matrices will come into play here. All right. So, like I said, today we'll talk about the transition matrices and similarity. But first, we want to see. We'll talk about the matrix for a linear transformation, and we're interested here in this one thing. Well, we have seen that. The matrix for a linear transformation from, let's say, T from a vector space V to itself depends on the basis for the vector space V. This is very important. We have seen that. Well, in other words, the matrix for T relative to a basis B, let's say, is different from the matrix for T relative to another basis B prime. And now we will ask the following problem. We want to solve the following problem, which can be stated as following. Determine whether it is possible to find a basis B such that the matrix for my linear transformation T is diagonal. So this is a classical problem that we would like to solve, and in fact we'll the solution to this problem will be discussed in the chapter with the eigenvalues and eigenvectors in the second lecture that will follow. It will be more related to the diagonalization of matrices. So we shall see how the matrices for a linear transformation relative to two different bases are related. So this is how what we want to do. And for here, I will denote four matrices, and you will see that there will be a relationship between them. So let me denote these four matrices, A prime, P, and P inverse. Already we're we're making an assumption here that P is invertible. So the determinant is non-zero. Like I said, P is invertible, and so P inverse exists. So these are the four matrices, and these four matrices satisfy the following four conditions. And I will better illustrate these four conditions when we'll draw a picture after I explain them. Well, as you can imagine, A is nothing else than just the matrix for my linear transformation T relative to the basis B. A prime is the same, is the matrix for the same linear transformation but relative to the basis B prime. And the transition matrices from one base to another, in this case from B prime to B, we have seen that it is this matrix P, and the transition matrix from B to B prime is P inverse. So these are the four matrices that we define. And for you to understand exactly what's going on, I will just draw your attention with the following. The following figure. Well, as you look at this, there are two ways to get from the coordinate matrix V relative to the basis B prime, as you can see it here, to the coordinate matrix T of V relative to the basis B prime. One way is the direct way, as you can see here, just by using the matrix A prime. But there is also an indirect way, if that we can do, is just to use the matrices P, A, and P inverse, right? We're going, as you can see, I'm starting from V, right? From the coordinates matrix V relative to the to B prime, to B prime, and then I'm going all the way to coordinate matrix V relative to B through and through matrix P, and then I'm going to T of V relative to B from the matrix A, and then from T of V to T of V relative to B prime, I'm going through matrix P inverse. So that's the indirect way. And in fact, we will have a relation here if we look carefully at this diagram, whatever figure, we will see that this matrix A prime will be closely related to these three matrices, to P, A, and P inverse. In fact, it will turn out that A prime will be nothing else than just P inverse times A times P. Anyway, so just like I explained, and if you look at the picture, this is very important, right? Okay, that's the picture. I'm gonna just leave it again to look at it. It's very easy to understand. In fact, the only thing you need to do is just to memorize this picture. I think and it's very easy to look at. Especially when you look at the arrows, it's quite logical. Just like I said, there are two ways to get from the matrix V, the coordinate matrix V relative to B prime, to the coordinate matrix T of V to B prime. Like I said, one way is direct through the matrix A prime. So we just multiply A prime by the coordinate matrix V relative to B, and we obtain T of V relative to B prime. And the other way is indirect, by just using these three matrices, just like I explained. And of course, we obtain that P inverse times A times P times the coordinate matrix V relative to B prime is nothing else than just T of V relative to B prime. And surprise or not, as you might expect, this A prime is nothing else than just P inverse times A times P, right? That's what it is. And in fact, this relationship, this equality, in fact, marked here in red, will be very important when we'll define what we call the similar matrices. We will see that A prime is a matrix that, well, A prime obtained in this way by multiplying by an inverse P inverse times A times P will be a matrix that is similar to matrix A. So A and A prime are similar. But anyway, we'll get there and we'll explain. Well, clearly, we'll illustrate this relationship between the two matrices, A and A prime, through some examples. And the first example I have in mind is the following. Look at this example. You see, you have a linear transformation in R from R2 to R2. And this linear transformation is given explicitly. As you can see, it is t of x1, x2 is 2x1 minus 2x2 and negative x1 plus 3x2. And I want to find a matrix A prime for this linear transformation relative to this basis. Look at this basis. It's a basis in R2. Well, it's kind of different from the standard basis. Well, not too much at first, but it's quite different. So we want to find this matrix. Well, what is the first thing we need to do? As you can see here, I need to find some coordinate matrices. So the standard matrix but first we want to write the standard matrix for the bilinear transformation. As you can, this is very easy to see. You just look at the coefficients from each component. There's a standard matrix for bilinear transformation T will be nothing else than just 2, -2, -1, and 3. Well, as you look at the coefficients here, right? There's -1 here, there is 3. It's easy to see. Anyway, so this is the standard matrix for T. And now we want to write a transition matrix from my basis B prime to, guess what? I'm going to use the standard basis B, which is given by this. B is what consists of these two vectors, 1, 0, and 0, 1. Well, these two bases, like I said, they're quite similar. The first vector is the same. The second one will differ. And you know how to find the transition matrix, right? I'll leave it to you as an exercise to figure it out that the transition matrix between from these two bases from B prime to B is given by this matrix P. So I'll leave it to you as an exercise to show this. In fact, we showed this, and if you go back to, I don't know what lecture exactly, but we showed this in the previous chapter, exactly this example. We took these two bases. But anyway, you can redo this as an exercise. Clearly, P is invertible. The determinant is 1, so it's non-zero. So the inverse exists. That's the first thing. Well, and now it's very easy to find A prime. Well, before we even, because we know that A prime, if you go back, look here, A prime is nothing else than just P inverse times A times P. So now that we know that the transition matrix P is invertible, we can find the inverse. And again, as an exercise, it's very easy for you to see that the inverse is given by this matrix here. So 1, -1, 0, and 1. Now, you can finish the problem. You can just write A prime. So for the linear transformation, for our linear transformation T relative to B prime, this matrix is given by this. So you just multiply P inverse with times A times P. So the multiplication of these three matrices, well, I have already done it, and I hope I didn't do any mistakes, is given by this matrix, right? Well, it's just a matter of exercise. I think yeah, it should be correct, I hope. All right, this is the first example. It was pretty straightforward. And as you can see here, I want you to look very closely because I related this basis to the standard basis. Was now the second example. I'm not going to do that. What I want is the following. I want you to look at the statement. as you can see here in this example, I have two bases for R2. So the first one is given by these two vectors, -3, 2, and the second vector is 4, -2. And my basis B prime is given by -1, 2, and 2 and -2. So these are two bases for R2. And now let's consider the following matrix for my linear transformation T. So given a linear transformation T from R2 to R2, I know how its matrix would look like. Well, the matrix is given by, it's a 2 by 2 matrix. Of course, it cannot be of any other order. It's given by -2, 7, -3, 7. And again, I want to find the matrix A prime, the matrix of my linear transformation T relative to B prime, because I know, given the fact that I know how my matrix A looks for my linear transformation T relative to the basis B. Again, this is pretty straightforward. And the transition matrix from B to B prime, and I'll leave it to you as an exercise, is given by this matrix. Again, I think we've done this example in one of our previous lectures. I'm not sure if I did it exactly for these two bases in R2, but something very, very similar. For sure we have done it. Okay, so the transition matrix from B prime to B is given by this. It's P, which has the entries 3, -2, and 2, -1. Right, I'll leave this to you as an exercise to see it for yourself, or if you don't want to solve this again, you can just go and see one of our previous lectures. Okay, so this is a transition matrix from B prime to B, right? And now we want to write the transition matrix from B to B prime. Well, again, it's very straightforward. We need to find the inverse. Clearly, this matrix is invertible. As you can see, the determinant is non-zero. And by an exercise for you, well, I have already done the computations. You can find the inverse for this matrix, which is given by -2, -1, 2, -2, and 3. So that's the inverse. Anyway, there are plenty of ways of finding the inverse of this matrix. I assume you already know this by now. Okay, and now it's quite clear. So the matrix for T relative to B prime, again, it's that A prime matrix, which is given by this product, P inverse times A times P. And again, I have to multiply these three matrices. And again, by this multiplication will give you this 2, 1, and -1, 3. Right? And we're done. So you see it's, again, this was straightforward. The only difference was that the bases were given. I already have given these two bases, B and B prime. So it was pretty straightforward. Now let's see another example, example number 3. And I want you to look at it very, very carefully. So the third example says the following: for a linear transformation T from R2 to R2, and again, the linear transformation is from the previous example. I want to find basically the transition matrices. So I want to find the transition matrix V relative to B, T of V relative to B, and T of V relative to B prime for the vector V whose coordinate matrix is given by this. Again, this is quite easy if you remember that what we said at the beginning. Let me go back. You see, we have this relationships here. This one and this one. And everything will just, because like I said, there are two ways of obtaining to get from the coordinate matrix V relative to B prime to the coordinate matrix T of V relative to B prime. And again, this comes down to this picture again, right? So you have to keep in mind this picture. So the only thing you need to know is this picture. You have to keep it in mind. And of course, how to obtain the transition matrix from one base to another, which we have already covered previously. That's it. There is nothing else you can. Okay? So you don't need to learn any formulas by heart. You just have to understand this picture. All right, with this in mind, we have these two relations, right? These two equalities here. And once we have this, well, the problem is pretty straightforward. So let's look at them. Okay, so we need to find the transition matrix of V relative to B, right? For this, we use the transition matrix from B prime, from the basis B prime to B. And again, this is given by this relation. And this is pretty straightforward. We just have to multiply these two matrices. So P is given by this, because we already know P, right? The transition matrix. Why we have found it? Look, the transition matrix from B prime to B is this matrix P right here. So we're going to write it. Keep in mind that we are using the linear transformation from example 2. This is all right. So we're going to do this computation. As you can see, I'm multiplying here a 2 by 2 matrix, and I'm multiplying this by a 2 by 1. So the result will be a 2 by 1. And it's just a matter of computation to see that this will give us this matrix, this transition matrix. It will be given by, it will be a 2 by 1 matrix, and it will be a -7 and -5. And now we're going to do the same thing. We want to find T of V relative to B, and we're just going to multiply V relative to B on the left of the matrix A. That's what we're going to do to obtain the T of V. So again, it's just another computation. It's just a multiplication. Again, the same story. I have a 2 by 2 matrix here, 2 by 1. And if you do the computation, I hope the computations are correct. This will give us the matrix, the 2 by 1 matrix, -21 and -14. Okay. And now we want to find T of V relative to B prime. We do the same thing. We multiply T of V relative to B on the left by P inverse. And again, the same story. Just a multiplication of matrices. Again, 2 by 2 with multiplied by a 2 by 1, and will give us this matrix. Again, this was pretty straightforward, and it boils down to this picture. Again, this picture. Keep in mind this picture. I want to stress this again. I will say it again and again. This is the picture you have to remember. Well, you have to understand. Let me put it this way. Okay. And these are the two equalities that you have to, well, you don't have to know them because the final exam will be a take home, but at least to understand them. So you can look for these two formula. Okay, I think now we can go towards our second part. And the second part will concern similar matrices. And you'll see that what we have discussed so far will play an important role in talking about similar matrices. In fact, without even mentioning, well, I already did, but I already told you explicitly actually what similar matrices is all about. Anyway, but we'll see the formal definition. As you can see, just like I said, two square matrices A and A prime that are related by this equation, and we have seen that there exist matrices which are related by this equation. A prime is P inverse times AP, are called similar matrices. Well, we have already seen previous examples. In other words, let me just give you the definition. Let me say it again. For square matrices A and A prime of order n, we say that A prime is similar to A when there exists an invertible matrix P such that A prime is P inverse times A times P. We will see, and I want to mention something here. We will see that these similar matrices will be very important when we will talk about diagonalization of matrices and eigenvalues. You will see that similar matrices basically have everything the same determinant, the same trace, the same characteristic polynomial, you name it. All right, so this is the definition. And now, as you can imagine, we want to talk about some properties of similar matrices. And the properties, I would say that they're quite obvious. They're given by this theorem. Right, if I have A, B, C square matrices of order n, then the following properties are true. Of course, the first one, A is similar to A, that's obvious. Then if A is similar to B, then also B is similar to A. And the transitivity, the third one, if A is similar to B and B is similar to C, then A is similar to C. Well, what you expect, well, quite, this theorem, well, it's not like anything that we did not expect. Now let me point out a remark. From the definition of similarity, so as you can see the definition here, look at it. So basically there exists an invertible matrix such that A prime is P inverse times AP from this definition. It follows that two matrices that represent the same linear transformation T with respect to different bases must be similar. Well, again, this is quite obvious from the definition. And now let's see some examples. And again, I'm going to take examples from our previous discussion. And as you can see, these two matrices here, A is 2, -2, and -1, 3, and A prime is 3, -2, -1, 2. These two are matrices. We have already seen that. We have exhibited a matrix, an invertible matrix P such that A prime is P inverse times AP. Well, guess what is this matrix? And now it's just a matter of computations for you to see that, but we have already did that, so we've seen it. Then now let's go back to the example number 2. Again, we have seen that those those two matrices A and A prime. So A is given by -2, 7, -3, 7, and A prime is 2, 1, -1, 3. Again, these two matrices are similar because, again, by the same token, this is there exists this invertible matrix P, which is given by 3, -2, 2, and -1, such that A prime is P inverse times AP, right? Again. And now I want to answer the following question. This is a very important question. Well, I'm going to be vague a bit, the first question, and then when I will address the second question, I'll be more precise. So the first question is, what choice of basis will make the matrix for my linear transformation T as simple as possible? I want to choose a basis so that I could write this matrix as simple as possible. Well, how simple can that matrix look like? And now the question two, is it always going to be the standard basis? So what kind of choice? Do I need to choose the standard basis always? Well, the answer, well, not quite like that. I'm going to give you the following example. And this time I'm going to consider a 3 by 3 matrix. This example will concern will provide a comparison of two matrices for a linear transformation. And this example would clearly demonstrate that the answer to question number two is not always true. So let's see. So the third example is I'm given this 3 by 3 matrix with the entries 1, 3, 0, 3, 1, 0, and 0, 0, -2. So this is the the matrix for my linear transformation T from R3 to R3 relative to the standard basis. We all know how the standard basis looks like, right? The standard basis, when I say standard basis in R3, I mean these vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? So that's what I mean by the standard basis. Keep that in mind. We have already talked about this numerous times about the standard basis. In fact, even for standard basis or vectors in Rn. All right. So I'm given this matrix, which is the matrix for my linear transformation T relative to the standard basis. Okay, that's information. And now I want to find the matrix for T relative to another basis, which is given by B prime, which consists of vectors 1, 1, 0, 1, -1, 0, and 0, 0, 1. All right, at this point it's quite clear what to do. The transition matrix from B prime to the standard basis has columns consisting of the vectors in B prime. Anyway, the transition matrix will be given by this. So it's 1, 1, 0, 1, -1, 0, 0, 0, 1. So like I said, has a basis, has columns consisting of vectors in B prime. And now it will follow that, well, clearly this is, I'll leave it to you as an exercise to show that the determinant of this is non-zero. So therefore, A is invertible. And once it's invertible, you can find the inverse. The inverse exists, and you can actually compute this. And the inverse, I'll leave it to you as an exercise. There are plenty of ways to compute this inverse. Is given by this. So P inverse will be 1/2, 0. That's the first row. The second row is 1/2, -1/2, 0. And the third row is 0, 0, 1. Okay, and now the matrix for T relative to B prime is clear what we have to do. Again, we're going to multiply 3 matrices. And the computation is right here. So we have this guy here, A prime, again, is P inverse times AP, and we have to multiply these 3 matrices. And according to the computations, the result is the matrix whose entries are the following. On the first row, we have 4, 0, 0. Second row, the entries are 0, -2, 0. And the third row, the entries are 0, 0, and -2. So this is my matrix A prime. And now note that something about this matrix A prime, you see? This matrix is diagonal. Right? Well, that's it. That's it. Now let me point out a remark here. Diagonal matrices have many computational advantages. That's why I want diagonal matrices. You will see that it's very easy to work with them. For example, especially when I want to compute the eigenvalues, it's very easy to write the trace of a diagonal matrix. It's very easy to write the determinant of the diagonal matrix. It's very easy to find the eigenvalues, as we shall see in the second lecture from the next chapter. So they have many computational advantages over non-diagonal matrices. For example, if we have this diagonal matrix here, D, as you can see it, it's, we have, of course, everything else is 0. It's only the elements on the diagonal, right? Or D1, D2, Dn. Then it's quite clear to compute the kth power. And the kth power, you can actually prove this by just multiplying D squared is D times D, and then you multiply by another D, and you keep going step by step, and you will see that D to the power K will be nothing else than just this. Right? You just raised the elements on the main diagonal to the power K. Also, another advantage for diagonal matrices, for example, a diagonal matrix is its own transpose. Another thing, moreover, if all of the main diagonal entries are 0, then the inverse, if all of the main diagonal entries of a diagonal matrix are non-zero, then the inverse of the matrix is also diagonal. It's a diagonal matrix, which is great. And its entries will be the reciprocal of the corresponding entries from in the original matrix, right? Well, there are plenty of computational advantages for this diagonal matrices, but like I said, we will study them in the next chapter. And I think this wraps up everything for this chapter. Finally, it just remained only this part, which is a very important part, the similarity, and also the how to write the transition matrices. I will do more problems when we will talk about at the review session. We'll talk more about this. You'll see how the similar matrices basically share many things in common. Like I said, the characteristic polynomial, the trace, the determinant, and so on. All right, I'll stop here. Thank you very much.